Okay, we're going to discuss a pretty straightforward idea of a function, whether a function has a maximum or a minimum, and if it's a absolute maximum or local minimum. So maximum, minimum are pretty straightforward ideas. If you look at this point right here, clearly this is a high point, and that's also a high point. These are all low points, 1, 2, 3. I guess they're labeled A, C, and E are all low points. The only difference is, obviously, this is the highest point. So we would call that an absolute maximum, also called a local maximum, but usually just give them one of the two names. So since this is the absolute highest point, you would call this an absolute maximum. Therefore, this one could be called a local maximum. It's also called a relative maximum as well. So relative and local are interchange, and I might interchange those words as I'm discussing them. Lastly, we also have minimums. So here is a local min. And here is also a local min, and then this is the absolute min, also called a local min, but we're just going to call it an absolute min in this case. These would be the endpoints, so you always want to check the function values on the endpoints of the interval. So this function f is defined on the interval from a to e, so it's on brackets, so therefore you would include the endpoints a and e. So you always want to check the function values on the endpoints to see if they're any lower or any higher of the other mins and maxes that you get. This min and this max, this max and this min are found by setting the derivative equal to 0. So you would take your derivative, set it equal to 0, and then determine the function values at these given values b and c, and see how low and how high they go. And then this one here, notice that it's a corner or a cusp. That would be where the derivative is undefined. So set the derivative when it's undefined, which usually is when you have the x in the denominator. You would want to check that value, that function value, to see how high it goes. And then these are when the derivative is equal to 0. And then these are the endpoints. Sometimes, so you notice on this one, the absolute max is on the interior of the interval. So it's in between a and e. So it can be in the middle of the interval, or it can be in the end of the interval. Notice that the absolute min is at the beginning of the interval or at an endpoint of the interval. So that's why you always check your endpoints and then check when the derivative is equal to 0 and when the derivative doesn't exist. So let's jump into an example. First example is a pretty straightforward looking parabola, x squared minus 4 on the interval -5 to 4. Let's take a look at the graph. Here's the graph right here. So notice that even though it has arrows on here, I've set it so it only starts at -5 and ends at +4. So that's how I put those little endpoints on there. Here's our function x squared minus 4. So it's just a parabola that has intercepts at -2 and 2. And notice we have a min at 0, -4. So how do we find these values? Well, -5, 21 and 4, 12 is just taking the endpoints -5 and 4 and plugging it into the function value. And then how we found this value here is we just took the derivative of the function, set it equal to 0, then took that value that you got, plugged it into the function, and you got -4. So the two things we do is check the endpoint function values. So -5, plug it in, 4, plug it in. Here, set the derivative equal to 0. Notice you have a horizontal tangent, so the derivative is equal to 0. Find that function value, and then compare them. So clearly this is the highest point, the absolute max. This is a local max. It's pretty high in this area. It's the highest point in this area, so locally it's the highest point. And this is the absolute max because it's the absolute lowest point on this total function interval, this interval of the function. So first thing I usually do is just take the derivative. So f prime of x is equal to 2x. I set my derivative equal to 0. I get x equals 0. And then I just evaluate the function at the endpoints. At the critical value, in this case, the only critical value we got is when the derivative is equal to 0. Also, critical values can be when the derivative is undefined. So plugging -5 in, so you'd square it -4. So that gives us 21. You plug 0 minus 4 is -4. You plug 4 in, you square it, you -4, you get 12. So this is obviously our absolute. So f of -5, 21 is an absolute max, 0, -4 is an absolute min, and 4, 12 is a local max. So it's helpful to know what the graph looks like in order to determine whether it is a local max or min. Obviously, it's pretty straightforward. That this is the highest point, that's an absolute max, and this is the lowest point, that's an absolute min. It's just not clear whether this is a local max or min. So that's obviously it's pretty helpful to know what the graph looks like. In this case, you knew it was a parabola, so you know that this had to be a local max point. Let's take a look at the next one. So again, okay, just made it bigger. So here is our function. In this case, it's a radical function. It's x raised to the 2/5 power. So it has a little different behavior than the parabola or any polynomial does. Let's take a look at the graph here. This is pretty interesting looking graph. So it has a very high point of negative 32, 84, because our interval goes from negative 32 to 32. So here's the bottom point, 32, negative 44. And then notice the function kind of comes down. It has a little cusp here, and then bounces back up. It has a maximum. So 0, 0 is the bottom of the cusp. Then we have a maximum at 1, 3, and then it goes down out to 32, negative 44. So how do we find 84 and negative 44? Well, we plug in the endpoint values. How do we find 0 and 1? So those are on the interior. The 0, 0, that would be when the derivative is undefined, and this will be when the derivative is equal to 0. So obviously taking the derivative is important in these problems. Plugging in 0 gives us the function value. Plugging in 1 gives us the function value of 3. So 0, 0 would be a local max, because locally this is the lowest point in the area. And this would be 1, 3 would be a local max, because locally in this area this is the highest point. I may have screwed up. I think I said max here. This is a local min. So derivative f prime of x equals 5 times 2/5 x to the negative 3/5 minus 2. The 5's cancel. So we get f prime of x is equal to 2x to the negative 3/5 minus 2. Whenever I have a negative exponent, I always write it in the denominator and then get common denominators. So I'm going to multiply this by x to the 3/5 over x to the 3/5. So we get f prime of x is equal to 2 minus 2x to the 3/5 over x to the 3/5. Let me get rid of the red. That's kind of ugly. So you set the numerator equal to 0. That gives us when the derivative is equal to 0. So f prime of x equals 0 when 2 minus 2x to the 3/5 equals 0. So add 2 over and divide. You get 2 equals 2x to the 3/5. X to the 3/5 equals 1. So x equals 1. And f prime of x does not exist when the denominator equals 0. And that's clearly when x equals 0. So we want to evaluate our function at negative 32, at 0, at 1, and 32. So when we plug those values in, they're not the easiest to handle. F of negative 32 is equal to 84. F of 0 is 0. F of 1 is 3. F of 32 is negative 44. So clearly this is an absolute min, and this is clearly the absolute max. So notice that from negative 32 to 0, it's decreasing down to 0. So this is a local min. And then from 0 to 1, it's going up a function value from 0 to 3. So therefore, this must be a local max. Also, we know that because we know what the graph looks like. It comes down, it bounces. So this is when the derivative was undefined. We said the denominator equal to 0, the derivative. Then it bounces back up, we get a local max, and then it goes out to the local min at 32, negative 44. Okay, here we have a piecewise function. It's essentially two parabolas where the pieces begin and end at 1 on an interval from negative 2 to 6. So here's our graph. So our first function is x squared plus 2, and our second function is 2x squared plus 2. So 2x squared plus 2. They begin and end at 1. So g of x, the second function, starts at 1, 4. The f of x ends at 1, 3. So there's a gap in between there too. It's just that since this function goes so far up, I had to squeeze it in a little bit. So there's obviously a gap in between there. So it's a point of discontinuity. and then the x squared plus 2, the first function, starts at negative 2 comma 6. And clearly there's a low point here, which is, I didn't do a very good job of where that point is. Let me pause that. So that's a little bit better. So it's at 0 comma 2, so that's a low point. So that's when this derivative is equal to 0. I plugged in the endpoints at negative 2 comma 6, so that's where the piecewise function begins, because our interval goes from negative 2 to 6. So we plug in 6, we get 74, plug it into the second function. And then since it's less than or equal to here and greater than here, this would be a closed circle. This blue one would be a closed circle. And I can't make this open, but this would be the open circle. Okay, so checking the endpoints, checking when the derivative is equal to 0, and then you'd want to check when the piecewise function goes from one function to the next. Since this is the closed circle, this would be a local max. Since this is an open circle, there wouldn't be a local max here local min, because it's an open circle. It's not defined at 1 comma 4, so you wouldn't really name this point at all. So just like always, I'm going to take the derivative, set it equal to 0, and then check the endpoints, and in this case, check the when the piecewise function goes from one piece to the other. So I'm just going to write the derivative as f prime of x, and then just write it as two separate functions. 2x when x is less than or equal to 1, 4x when x is greater than 1. So let's set the derivative equal to 0. There is no time in which the derivative is undefined, and so far, except when it's discontinuous, and we'll deal with that later. F prime of x equal to 0, so 2x equals 0 when x equals 0. So that's in this interval between negative 2 and 1. So therefore, that is a point in which the derivative is equal to 0. Setting the other function equal to 0, 4x equals 0, the other derivative, we get x equals 0. However, that's not in this interval, so that one is not helpful. So we want to check at negative 2, and then we want to check at 0, and then we want to check at 1 when the piecewise function goes from one piece to the other. We'll make this 1 from the left-hand side and 1 from the right-hand side. And then we want to check at 6. So let me write down all those function values for you here. So here are our function values. But just one note that since this is greater than, not greater than or equal to, the right-hand value at 1 is of no help, so therefore we're not even going to consider that point. So since this 2 is the lowest function value that we have, we'll call this an absolute min, and likewise this is our absolute max. So now since it goes from 6 down to 2, we'll call this 6 a local max, since our function values are decreasing, and then since it's going from 2 up to 3, we'll call this a local max. And we can verify that again by looking at the graph. This is a local max, absolute min, local max, absolute max. And that's verified here. So here we have a parabola, and then we have a couple different intervals here. We have the closed interval from 0 to 2. We have the closed and then open interval. So 2 is not really going to be an interesting point because it's up to but not including 2. So that point won't be a local max or absolute min. And then here we have the same thing, except it's opened on 0 and closed on 2. And then lastly, we have an open circle on both sides. So therefore, neither one of these will be critical points because the function is not defined at 0 nor at 2. So just like all the other problems, we want to consider when the derivative is equal to 0, and then we'll consider the endpoints and discuss max and mins. So f prime of x is equal to 2x minus 4. Set the derivative equal to 0. I get 2x minus 4 equals 0, and I get x equals 2. So it looks like we'll have a local max or a min at 2. Let's look at the graph. Not a very interesting looking graph. Here's x is 0, and our function value is 5. And here is 2, and the function value is 1, and here's our function right here. So it just goes from here down to here. And so since sometimes this is closed and sometimes this is closed and vice versa, sometimes open and open, that's going to change what we have. But ideally, if this is a closed interval on both sides, we have a local max right here, an absolute max up here, and an absolute min down over here. So we just need to determine, given the type of interval we have, whether we have absolute max or mins at those intervals, at those points, So f of 0, we already know is 5, and since it's a closed, that would be a absolute max. And f of 2 is equal to 1, so that's an absolute min, and f of 2 is at the end of our interval, and this also happens when the derivative is equal to 0, so we've double duty there. So the only critical point we're going to have in this one is when we have f of 0 is equal to 5, so that's an absolute max, and we can't consider f of 2 because it's an open interval and it's not, the function's not defined at 2. Likewise, the only function value we can evaluate, or the only endpoint we can evaluate, is 2. F of 2 we've already determined is 1, so that'll be our absolute min. And here there's no min or max since the endpoints, the function is not defined.